Hello there. In this video we're going to discuss some important properties that are associated with logarithms and logarithmic functions. So first off, recall the three basic properties associated to exponents. The first one, if the bases of the two exponential relations are the same, so let's assume that a is equal to b in that case, then you can simply add the exponents and keep the base the same. Similarly, if you divide these expressions with the same exact base, then you can directly subtract these exponents. And if you have a power raised to another power, then you can multiply these powers together. In this video, we're going to develop about 4 properties that are associated to logarithms, which are pretty much parallels of these. Alright, so to get started, what we want to do is remember the connection between exponential and logarithmic relations. So if a to the x is equal to b, then in terms of logarithms, this is the same thing as saying the log base a of b is equal to x. Similarly, if a to the y is equal to c, then this is going to imply that the log base a of c is equal to y, right? So therefore, a to the power of x plus y, if this is equal to d, then this is going to be equivalent to saying what? Well, that's going to be the same as saying the log base a of d is equal to x plus y, right? So remember that a to the x times a to the y is the same thing as a to the power of x plus y, right? So this is equivalent to saying what? Well, a to the x is b, a to the y is c, and a to the x plus y is equal to d, right? So this is pretty much the same thing as saying b times c is equal to d in terms of these expressions that we have above, right? So let's just keep that in the back of our mind just temporarily. So let's look at these three relations that we have here. So we know that x plus y, so x in this case is going to be log base a of b plus the log base a of c, and that's of course going to be equal to the quantity x plus y, which in this case is going to be equal to the log base a of d, right? But remember that d is the same thing as b times c, right? So we have log base a of b plus log base a of c is equal to log base a of d, but substituting that expression here, then we're going to have that the log base a of b plus the log base a of c is equal to the log base a of b times c. So a, b, c, and d are all arbitrary letters or variables or values, so we can just rearrange or rename these objects to give us our first rule. In particular, the log base a of x plus the log base a of y is equal to the log base a of x times y, right? So when you add two logarithms with the same base, then you can multiply their interiors inside of the logarithm with the same exact base, right? So that's the parallel to the first exponential rule. So what about subtraction? So similarly, so we can say, okay, a to the x is equal to b, a to the y is equal to c, and we know we can define, well, a to the x minus y to be equal to d, right? So therefore, a to the x over a to the y, right, which is of course a to the power of x minus y, which is equal to b over c, which is equal to d, right? So we can define, similarly as before, log base a of b to be equal to x, log base a of c to be equal to y, and the log base a of d to be equal to x minus y, right? That comes directly from these expressions. So therefore, if we take the quantity x minus the quantity y, that's going to be equal to the log base a of b minus the log base a of c, which is going to be equal to the log base a of d, right? Which is, of course, equivalently the quantity x minus y, right? Now we can use the relation that d is the same as b over c and replace that here and get a rule there. So that means the log base a of b minus the log base a of c is the same as log base a of b over c, right? So renaming all our variables to get our second rule, we have the following. So if you have a logarithm of base a of some parameter value x minus the same logarithm with a different parameter y, or it could be the same, then this is going to be equal to the log base a of x over y. So when you add logarithms, you multiply the interiors. When you subtract logarithms, you divide their interiors, making sure that, of course, these logarithms have the same exact base, right? Going back to the addition rule for logarithms. So we have log base a of x plus the log base a of x. And let's assume we add to this log base a of x, and let's assume this is n times, right? So if we add together n logs, then by the first property, this is going to be the log of x times x times x times all the way out to x, where there's n of these x's. And by properties of exponents, that's just the same as the log base x to the power of a, right? And these are all log base a's. But also notice if we add something to itself n times, then this expression is actually precisely equal to n times the log base a of the thing, or n times the thing for which you're adding, right? So this gives rise to another property. And of course, this proof is based on the fact that n is a natural number, but we can extend that to the reals using some properties that we'll discuss later, right? So this gives rise to our third relationship, that the log base a of x to the power of y is equal to y times log base a of x. So every time you have a power on the interior of the parameter, you can pretty much bring that down as a coefficient of the logarithm, which is interesting. All right. So just a quick reminder on some of the special logarithms in case you don't remember. Ln of x, which is sometimes called the natural log of x, is defined to be equal to the log base e of x, right? Where e is that special number 2.71828 and so on. Sometimes log of x is used as log base 10 of x, the base 10 arithmetic that we usually learn. Sometimes you may see lg of x, which some people refer to as the log base 2 of x, or the binary logarithm. You may see these two notations flipped around in some context or literature, so make sure they're talking about the right log with the right base for whatever purpose that you plan to deal with. All right, so again, recall, since logarithms and exponentials are inverses, the log base a of a to the x is equal to x, and a to the power log base a of x is equal to x. So this is another way of writing f composed of g of x equals g composed of f of x is equal to x, right? For all x in the common domain of f and g, right? So that's the definition of inverses. Right, so those are the inverse properties. So now let us see if we can derive another property that can sort of relate different logarithms with different bases, right? So I'm going to define log base a of x. I'm going to call this alpha. And let's consider log base a of y, and I'm going to call this beta, right? So if these two things are true in exponential form, that's the same as a to the alpha is equal to x, and a to the beta is equal to y, right? So what I'm going to do is I'm going to divide these expressions out and see what I get. So therefore, log base a of x over log base a of y is equal to alpha over beta, right? And we can divide these two expressions to get another expression. So we can have a to the alpha. So what does we get? Let's see. Actually, what I want to do is I want to apply logarithms to this expression. So I'm going to take the natural log of a to the alpha, so that's going to be equal to the natural log of x, and I'm also going to have the natural log of a to the beta, and that's going to be equal to the natural log of y. And you're going to see what I'm doing in a minute here. So if I have this expression, so using our power rule for exponents, I can bring these exponents down in front of the logarithm. and that's going to give me a natural log of alpha natural log of a over beta natural log of a, and that's going to be equal to the natural log of x over the natural log of y. Now notice a is an arbitrary number, so these two things cancel. So therefore we have alpha over beta is equal to the natural log of a over the natural log of x. Notice alpha and beta, I have not changed the definitions, so this expression and this expression are precisely the same. That means their other equation side are also the same. So therefore, the log base a of x over the log base a of y is actually equal to the natural log of x over the natural log of y. So you can write any quotient of logarithm as a quotient of natural logs or pretty much any other log for that matter, right? So for example, if you have the log base 2 of 3 over the log base 2 of 7, this is the same thing as the natural log of 3 over the natural log of 7. Those are equal values, right? All right, so going back to this general property here, I'm going to let y be equal to e, right? Because that's pretty much a special property associated with the logarithm. So if I let y be equal to e, then the natural log of y, which is the natural log of e to the first, is just equal to 1, right? So that means what? So that means the log base a of x over the log base a of e is equal to the natural log of x, right? So I'm going to multiply both sides by the log base a of e, and that's going to give us the log base a of x is equal to the log base a of e times the natural log of x. So what does that mean? Well, I don't exactly know what the log base a of e is, so I'm going to call this some number, say gamma, right? So if the log base a of e is defined to be equal to gamma, right? So what can I do? So then, let's see. Using this in exponential form, I can rewrite that as a to the power of gamma is equal to e. And then I can multiply both sides, or take the logarithm of both sides of this equation. So the natural log of a to the gamma is equal to the natural log of e. And I can bring this power down in front, right? So that's going to give us gamma times the natural log of a is equal to the natural log of e, but the natural log of e is just 1, right? So that means gamma is just precisely equal to 1 over the natural log of a, right? So that's pretty much the same exact thing, which is useful, right? So we can go back to this expression that we had before. Let's see. So we can go back to this expression here, or moreover this expression here, that's where we define gamma, and then we're going to have the log base a of x is equal to the natural log of x over the natural log of a. So we've expressed just the general logarithm as the quotient of two natural logarithms, right? So that's extremely useful. Notice the base of the logarithm is on the bottom of this denominator, and the interior of the logarithm is on the numerator of this expression. And this is sometimes referred to as the change of base relationship for logarithms, which in general, so you can call this the fourth property of logarithms if you want. So the log base b of a can be rewritten as the natural log of a over the natural log of b. So this is just an introduction to the properties of logarithms and a proof for each of these values, just in case you're curious where they come from. In the next video, we're going to go through several examples to illustrate how you can use these properties to rearrange, deconstruct, and construct logarithmic expressions of various types. Hope you enjoyed.